Namaste everyone, welcome to second PUC physics class. We were discussing about electromagnetic induction, right? Namaste, welcome to the class, hope you are doing well. We discussed about Faraday's laws, we discussed about Lenz's law and motional EMF. We were in motional EMF. You know that for the production of induced EMF or current, the very much needed thing is change in the magnetic flux, and that change in the magnetic flux can be brought in many ways. One, and you know the formula for flux linked with any coil or any closed circuit. Flux linked with any coil or closed circuit, phi b, is equal to number of turns in the coil, area of the coil, strength of the magnetic field passing through the coil, and with what angle normal to the coil will make it with the magnetic field. Right? If a coil is held like this, and if its normal is like this, and if the magnetic field is lying like this, this is theta. And if the and always define B as theta as the angle between the normal to the coil with the magnetic field. You will be very easily trapped in the final exam or in any exam. They will give you a coil is making an angle of 90 degree with the magnetic field. Don't put theta is equal 90. Coil is making an angle of 90 degree with the magnetic field. Magnetic field is maybe represented like this, and if it is in this direction situated, and if the coil is perpendicular, plane of the coil is perpendicular to the magnetic field, what about the normal to the coil? It is parallel to the magnetic field, either theta 180 or 90. It is not 0. Sorry, it is 0. Sorry, theta 0 or 180. Sorry, theta is either 0 or 180. It is not 90. Because normal to the coil is parallel to the magnetic field. But if the coil is like this, of course, if the plane of the coil is parallel with the magnetic field, normal to the coil is perpendicular to the magnetic field, theta is 90. So you must be very careful. And the change in the magnetic flux can be brought about by many ways. Change the number of turns in the coil. Let us see how to change it. Change the number of turns in the coil. Change the area of the coil. This is what we are going to concentrate now. Change the area of the coil and change the strength of the magnetic field. You can vary the magnetic field by bringing a magnet very close to the coil, taking it away, by changing the orientation. Keep the magnet here and turn the coil like this. When you turn the coil, the angle of orientation changes. When the coil is exactly in front of the magnet, maximum flux passes. When the coil is like this, minimum flux passes. You can change it like that way also. So change in the flux can be brought in changing the number of turns, strength of the magnetic field, area, and orientation. We will concentrate on this. That is motional EMF. So what you have to do for motional EMF? You have to take a frame, metallic frame like this, and that metallic frame is placed in a magnetic field, uniform magnetic field. What is this type of magnetic field? It is a magnetic field which is entering into the board. Into the board is represented by cross. Out of the board, a dot with a circle. Out of the board, magnetic field. Into the board, like this. So here onwards you have to represent the magnetic field like this. Into the board, out of the board. So this is into the board. And where is the north pole? North pole is here and south pole is on the other side. You know that magnetic field lines always start from north pole and end in south pole. This is north and south, like this. So here it is into, here it is out of the north pole, like this. So this coil is placed in a uniform magnetic field which is normal to the plane of the paper. Now this is not a closed circuit. It is not a closed circuit. Yeah, we will close it by putting another rod just over this. They are electrically in contact. Yes, we'll put it, and I will call this rod as PQ and the frame as RS. Now it is closed. What is the area? Length of the rod, I will call this as L into breadth X. That's all. Now, is the area constant? No, it is changing. Why? Because this rod is moving with a speed V. Let us move it with a speed V so that this contact is not lost. Contact between this C-shaped rod and this metallic rod is not lost anywhere. Right? Shall I switch on some bulbs here so that I will have enough amount of light? I have, but still sometimes it will not be enough. Yes. Now, okay, so the rod PQ is moved towards the left side, that is minus x-axis with a speed v. And what is the EMF induced? And now you know that the area of the coil goes on decreasing. Because of the change in the area, the number of magnetic field lines passing normally through the area go on changing, and that induces an EMF, and the motional EMF is given by Faraday's law. What does Faraday's law say? According to Faraday's law, magnitude of induced EMF is directly proportional to rate of change of flux, or it is equal to rate of change of flux. Negative sign is because of Lenz's law. Lenz's law we have seen, right? It opposes the cause, that we have seen already. Minus d phi by dt. Now, what is phi? Phi is nothing but this one, but here n is equal to 1. We have only one frame, right? One frame, only one turn of the coil. So, A, B cos theta. So, shall I write E is equal to minus d by dt of, this is over once, minus d by dt of A, B cos 0. Why cos 0? Normal to the coil and the magnetic field, both are in the same direction. It is not the angle between the coil and the magnetic field. Normal to the coil and magnetic field, both are in the same direction. Theta is 0, cos 0 is 1. This is 1. Now write the area. What is area? Induced EMF is equal to minus d by dt of. Area is length into breadth, L x b. B is magnetic field. Now, what is that varying in this? Neither L nor B. The magnetic field is uniform. Only flux linked with the coil keeps on changing. As you move the rod, it is not the magnetic field which is varying. Magnetic field is constant. The magnetic field passing, flux passing through the coil keeps on changing. That is because of this motion. X keeps on changing. X is the variable. So, shall I write the constant outside BL and differentiate only X? Because X is the variable. What is dx by dt? Dx by dt is the rate at which this distance decreases. That is the velocity. Since this, okay, E is equal to minus. So, shall I write this as B, L and minus dx by dt. Minus dx by dt is taken as V because it is moving in the negative x-axis. So, what is the induced EMF? Induced EMF is BLV, where V is the speed, uniform speed with which the rod is moved. Okay, that we have derived already. We know this one. Now, the next step. Using this, can you prove Lenz's law again? That is what I want. Or, okay, before that, we can derive in one more way about this induced EMF. Another way using the force on a charged particle moving in a magnetic field. Now, sir, where is the charged particle moving in a magnetic field? When you move this metal rod PQ, it contains plenty of charged particles, right? Free charges. All of them must experience a force. And that force must make them to move in one direction, either downwards or upwards. So, this induced EMF can be measured or calculated in another way, that is force acting on a charged particle moving in a magnetic field. Now, if Q is the amount of charge in this rod which is moving in this direction, then I can write Q as force acting on a charged particle moving in a magnetic field is QVB sin theta. Where is theta? Theta is the angle between the direction of motion of the charged particle. For example, I will take positive charges inside this rod. Actually, metal rods contain free electrons only. There are no free positive charges. There are positive charges called protons, but they are inside the nucleus, very firmly attached, not easy to remove. So, positive charges are not found, but still, of course, I can take the motion of positive charges, assume that positive charges are moving opposite to the direction of electrons. Okay, these charges are moving like this, magnetic field is inside. What is the angle between the magnetic field and the direction of motion? Q into V cross B. Oh, B I haven't written. QVB sin theta. Actually, it is Q in F is equal to Q into V cross B. Q into V cross B. Okay, VB sin theta. Now, theta is 90. Here, theta means angle between the direction of velocity and magnetic field. V and B, cross product, that is 90, F equal to QVB, right? Now, we have a definition for potential difference or induced EMF. Induced EMF is the work done in taking a charge from one point to another point. As you move the rod like this, with a uniform speed, each charge inside the rod will experience a force. And if you want to know the force direction, you can apply Fleming's left hand rule. If the first 3 fingers of the left hand are stretched mutually perpendicular to each other, with 4 fingers showing the direction of magnetic field, thumb showing the direction of force finally, middle finger showing the direction of motion of positive charges or current. Now you see, charges are moving towards the left, right? Okay. I have to apply it. 1 minute. The charges experience a force, right? The motion of the charges, middle finger. Forefinger magnetic field. Thumb shows the direction of force. Is it like this? Shall I show it like this, right? Magnetic field inside the board. Motion of positive charges, middle finger. Force acting on the charged particle downwards. So all the charged particles should move downwards like this. Positive charges. Of course, electrons should move upwards. And you know that positive charges always move from higher potential electric field to the lower potential electric field. They move from higher potential to lower potential. If all the positive charges experience a force downwards like this, then there should be a higher potential here, lower potential here. Otherwise, how come they move like this? Of course, you can explain it in different ways. Because of induced EMF, they move. What is induced EMF? What is potential difference? It is the work done in taking the charge. So, shall I write the induced EMF formula as work done in taking the charge, Q amount of charge? So all the charges, positive charges experience a force downward since they are moving in this direction along with the rod, because as the rod moves, charges should move. There is no difference in that. So W by Q. Now shall I expand W as force into displacement divided by Q? Right? I'll write this as displacement, otherwise I'll confuse with another X. Force into displacement by Q, induced EMF is equal to force acting on the charged particle is QVB, right? Because sin theta is sin 90, charged particle motion, magnetic field, and F into displacement. How much displacement will be experienced by these charged particles? It is L, right? From here to here, same as this one, P to Q, it is L by Q. Q gets cancelled. Induced EMF is B, V, L. Finish. Very simple argument here, right? So you can derive induced EMF, motional EMF as BVL by using force acting on a charged particle as well as the definition of potential difference. Definition of potential difference says it is the work done in taking the charge. Work done is force into displacement, force acting on the charged particle through a displacement of L, so you can get BVL. That's one part. Now, you can use this formula in Lenz's law, proving Lenz's law. Now, Lenz's law says that whenever there is a change in the flux, there is an induced EMF in a closed circuit, and that induced EMF generates a current called induced current, and that induced current should flow in such a way that it should oppose the cause that has produced it. Which is the cause? Change in the magnetic flux. Why the magnetic flux has changed? Either by moving the magnet or by rotating the coil, anyway. So that mechanical arrangement is opposed. Similarly here, when you move the rod, there was a change in the area. That change in the area produced the change in the magnetic flux. Finally, that motion which has produced the change in area or change in the magnetic flux, that motion should be opposed by the induced EMF. How? By developing a current here, and that current produces an heat energy. So heat energy produced by the current flowing through this induced current, and the work done, the rate of work done in moving this must be one and the same. Then only Lenz's law is true. Whatever the energy is spent per second in moving this and how much energy is lost per second in the form of heat must be same. That's what we have to prove it. Electrically, we have to take the formulas and you have to prove it. Okay, sir, how do you prove that? Okay, I will take it. I will rub this, I will use this space. Right, very simple. Now, if induced current is flowing in this rod because of the change in the area, because of change in magnetic flux, because of induced EMF, if there is induced current, let me take R as the resistance of this rod. When a current I flows through the rod of resistance R, you know Ohm's law? Induced current I is equal to E by R. What is the induced EMF from here to here? Of course, current flows like this. Here the current flows like this. In this part, current is like this, from P to Q, higher potential to lower potential. Here it is like this, higher potential to lower potential. Right? Here should be the higher potential because positive charges are moving from here to here. So from higher to lower potential. I is equal to E by R. Okay. Current is what is induced EMF? BLV by R. R I'll write. So I is equal to BLV by R. Let it be ready with us. Equation 1. So current, induced current is given by the EMF developed, potential difference divided by the resistance of the path. So this resistance of this path is R, BLV by R. Now, how much heat may be generated by this current? Right? I. You know, heat energy generated has a formula, I squared R, or power we will calculate. Power generated in the form of heat. Power is equal to I squared R. And you know many formulas for power. Power is equal to VI, put V equal to IR, I squared R, V squared by R. We will use I squared R formula because we are ready with the I, current, induced current. So what is the power? Power is equal to I squared BLV by R whole squared. Oh, R. I've used this as a common formula. Here resistance is small r. So what is the answer? Power generated, heat generated per second is equal to square this B square L square V square by R square into R. 1 R gets cancelled. So power dissipated in the form of heat B squared L squared V squared by R. This is the amount of heat generated per second. This has been developed because of induced current. Induced current has been developed because to oppose the work done, the cause, the movement, right? What is the power used to move it? That should be equal. They should oppose one another, means the total energy consumed per second must be same. So what is the power needed to move the conductor away? Because, and remember here, one thing, you have to move this conductor with a uniform speed, right? That means there is a force which is opposing you, that is developed because of that induced current, and that against that opposition force you have to move this, right? Power is equal to force into velocity. You have that formula. Power is also equal to force into velocity. Now which force is objecting you to move like this? Now this is a current carrying conductor. Now just think of what are the effects, one countering the other. This is a current carrying conductor. There is an induced current, and that current carrying conductor is placed in a magnetic field. It should experience a force, isn't it? Any conductor carrying current should develop a force, or it should experience a force when placed in a magnetic field. That current may be because of the motion, because of the change in area, because of change in flux. Okay, whatever it is, one is linked with the other now. Since this is a current carrying conductor placed in a magnetic field, it should experience a force. Again, Fleming's left hand rule. It will be like this. If I is the current taken by the conductor and magnetic field is inside, the force is like this. Against that force, you have to apply a force and bring it back in the uniform velocity. Because if you are alone applying some force on this conductor, what would have happened? Any force will not make the body to move with uniform speed. It will make the body to move with the acceleration. But we say that it is moving with uniform speed. That means a body moves with uniform speed when the net force on it is 0. How come the net force on it is 0? As soon as you move it, there is an induced current in the conductor, and that develops a force on the other side. So in order to balance that force, you have to apply a force, make the net force 0 and make it to move in the uniform speed. Only when the net force acting on a body is 0, it moves with uniform speed. You know that? Okay, so we will apply a force against the force developed because of the conductor carrying current. And you know what is the formula for the force acting on a current carrying conductor placed in a magnetic field? BIL sine theta. Again, theta is 90 here. Why? Because it is a current carrying conductor, current is inside, downwards, magnetic field is inside, 90 degrees, sine 91. Only BIL. L is okay, same L. I is current, that is this current, and B. Now let me write the power consumed, power used in moving it, and power generated in the form of heat is already being packed now. Yes, we have that formula. What is the power generated? Force into velocity. Force that you need to apply in the opposite direction is against this force, BIL sine theta. Okay, BIL I will write because sine theta is sine 91. BIL, velocity V expand I. Power needed is I. Which is that I? Current carrying conductor I. I is this one, BLV by R. V. BLV by R. I is over. This is I. BIL. I into L cross B. That formula. BIL sine theta. BIL. B. I is over L and V. What is the power used to move it mechanically is B square, L square, V square by R. Is it not same as this formula? It is same. So that's how we can prove Lenz's law here. Not a very important problem or a very important derivation for the exam except this derivation. This is very, very important, motional EMF. Derive an equation for motional EMF. They don't mention the way in which you have to do, but you prefer the first one because you have to use Lenz's law. Using Lenz's law, derive an equation for motional EMF. d phi by dt, phi changes with the area, so area has to be, in area x has to be differentiated because x is the only factor which is changing with time. Derive it. But this you better study it because it is a beautiful proof for Lenz's law. So we prove that Lenz's law is true. So the mechanical energy used to move this conductor is dissipated as heat energy by opposing it. Because that heat energy is generated by the current, they called induced current. That induced current is produced because of the reason of motion itself. So one counter arguing the other one, right? I don't know who is supporting who now, whom. Nobody is supporting nobody here, right? Everybody is arguing with everybody. So something finally you can see here, that is induced EMF and induced current. That's all. So very important part to know yourself for entrance exams and also for the complete understanding, or not complete, to the maximum understanding of this. This is very much needed. Okay, now we will go to another concept called eddy current. Very simple one, and 1 or 2 marks question, very easy questions. If at all you are selecting some questions in 2 marks part in the final exam, better you select questions from eddy current. And this derivation is 3 marks. Motional EMF derivation is for 3 marks. Okay, what is eddy current? EDDY. You know what is eddy? Eddy means some circular motion of water is also called eddy. Suppose if you look into a small stream of water moving, and wherever there is stone, water will circulate somewhere and it will form an eddy. In Kannada we call it as suli, right? Suli anta heltare kannadalli. Adu eddies adu, right? They are eddies, circular waveforms formed in water, right? Similarly, we have eddy current in here in metals. What you have to do is, we have to take a strong magnetic field. Say this is a north pole and this is a south pole. And you know that magnetic field starts from north and ends in south. That is outside. Inside the magnet also it moves. It exists. Now, you take a metal plate like this. Okay? You just keep on making it to oscillate like this. If a metal plate is made to oscillate, this is a metal plate. It is made to oscillate. It is made to go into the magnetic field, out of the magnetic field, into the magnetic field, out of the magnetic field like this. When the magnet is here, S enters, comes out, like this. What is the fate of this metal? Now, can you assume metal piece to be made up of many metal rods kept side by side? You can have many metal rods kept side by side like this. Can't you have a metal plate like this, right? Like this. When they are connected like this, you will have a metal plate. Now, all these are metal rods moving in a magnetic field. Whether it is a constant magnetic field is constant, but they are entering and maximum magnetic field passes through the coil and it comes out. So it is not a coil, but still it can be assumed to be a coil. Suppose you have a long wire wound into a coil. Just squeeze it and just make it flat. Then it becomes a plate. A plate contains many wires wound inside, right? You can assume that this is made up of many wires wound inside. So when a mass of metal is made to move in a magnetic field, entering the magnetic field or going out, and again entering, coming away in the opposite direction, small eddies of current, small circles of current, loops of current, that is a better word. Small loops of currents are produced inside like this. So like this, inside the metal. So when a mass of metal is moved in a magnetic field, when it is taken into the magnetic field and taken out, there is a change in the flux linked with the metal plate, and that induces small circular loops of current inside the metal, and that circular loop of current is called eddy current. Eddy currents are it is nothing but EMI. There is no difference between this and EMI. That is exactly the EMI. So when what do you mean by eddy current? The small loops of current produced in a metal when that mass of metal is moved in a magnetic field, that is called eddy current. The loops of current produced, small circles of current produced, small circular loops produced inside the small circular current loops produced inside a metal when it is moved in a magnetic field are called eddy currents. And now suppose you have a pendulum like arrangement like this, like the pendulum of a clock made up of a metal. You just make it to oscillate in a magnetic field like this. What happens is, 1 or 2 oscillations, it comes to rest. Very soon it comes to rest. Why? Again Lenz's law. It doesn't oscillate as if you do a pendulum experiment in your first year PU. If you just make the pendulum to oscillate, it keeps on oscillating for a long time, isn't it? It takes the same time for one oscillation. Here it is not like that. It oscillates, and as it enters the magnetic field, the speed decreases, stop. Because as it enters the magnetic field, the magnetic flux linked with the metal plate goes on increasing. And as the magnetic flux changes, there is an induced EMF. And that induced EMF produces eddy currents, and these eddy currents will flow in such a way that they oppose the cause. Which is the cause? Motion, oscillation. Oscillation itself will be stopped. So oscillations are damped. So if you have it in a machine, for example, in some machine, say there is an oscillating rod, and suppose that oscillating rod is situated very close to a magnet, what happens? Now that oscillating rod, it will find it difficult to oscillate, because as it oscillates across the magnetic field, eddy currents are produced inside. These eddy currents oppose the motion of that part, and that part finds it difficult to move, and lot of energy is wasted. So damping of oscillations of a pendulum is because of the eddy current. It is a loss. And one more loss, very heavy loss for us, eddy current loss. That is, usually, you know that ferromagnetic materials are very good magnetic materials, and if you have a magnetic field like this, right, uniform magnetic field like this, you simply bring iron piece or ferromagnetic material and keep it here. What happens to the magnetic field lines? If a ferromagnetic material is kept in a magnetic field, all the magnetic field lines get shrinked like this. They concentrate. Ferromagnetic material concentrate the magnetic field lines. And so hence the intensity of magnetic field increases. That is the famous use of ferromagnetic materials. The magnetic field, instead of spreading everywhere, it intensifies, and suppose you want a coil to use magnetic field. If you place the coil here, what happens? That coil does not use these magnetic field lines, right? It is wasted. Instead, we want to use this magnetic field also to get concentrated in the region of the coil. What you can do? That coil is usually placed around a ferromagnetic material, cylindrical ferromagnetic material. Suppose this is the frame of the galvanometer. I am coming back to the galvanometer, and here is the cylinder. This is a solid cylinder made up of ferromagnetic material, because if you have the magnetic field created by north and south poles of a magnet, all these magnetic field lines get concentrated in the region of the coil. So it intensifies the magnetic field. Remember, ferromagnetic material doesn't produce extra magnetic field, it intensifies, that's all. And of course, the strength of the magnetic field increases in that region. Now, in the same reason, we have an arrangement in the that transformer. What is a transformer? Transformer is a coil. Two sets of coils. One is primary, another is secondary. We are going to study about transformer in detail later. It's a set of coils, primary and secondary. When AC is applied to, because it also works under electromagnetic induction. Principle of transformer is electromagnetic induction. When you pass an AC to the primary of the coil, the primary of the coil produces a magnetic field. Since it is AC, you know that AC continuously changes its sign. It increases, decreases, becomes 0, minus and everything. The magnetic field produced by this coil will be increasing, decreasing, becoming 0, negative, maximum 0. As the magnetic field is changing with time, the magnetic field linked with this coil also changes. So that induces an EMF. An EMF is induced in the secondary. This is the main principle of the transformer. Change in the magnetic flux of one coil, change in the magnetic field produced by one coil induces an EMF in the other coil. They are not at all connected by any wire. They are simply placed close together. Now, this is what I have shown, the magnetic field lines, right? They are not connected actually. Okay, now, in order to intensify the magnetic field produced by the primary coil may be wasted. This magnetic field doesn't get linked to the secondary. What I can do? I have to place iron core. In a transformer, usually primary and secondary coil are wound on a core, that is a iron base. Actually, it is like this. Of course, I am giving all the explanation of the transformer, but still, when it comes actually to the explanation of transformer, I will cut short all these explanations. You will have a very heavy block of iron, and to this block we wind primary and secondary coils like this. So these are this is primary, this is secondary. Why, sir? Because this iron block, it intensifies the magnetic field. But the problem is, when you pass an AC to this, there is a varying magnetic field produced, and our aim is to link it to the secondary. That's why we wound both the primary and secondary coils into an iron core, right? Iron block. So that iron block doesn't waste the magnetic field lines like this. It will intensify all the magnetic field lines and more magnetic flux is linked with the secondary. That was our aim. But what happens? This is a ferromagnetic core, and this is under varying magnetic field now. Whenever a mass of metal is moved in a magnetic field, or metal is fixed, only magnet is moved, one and the same. You need not move the metal piece only. You can move the magnet like a swing, right? That is also possible. Bring the magnet closer to this or move away from it. That is also possible. So, if you do such things here, when a change in the magnetic field is produced by the primary coil, this metal block induces eddy currents. Eddy currents are produced in the metal block. Many eddy currents, small loops of current are produced inside the metal block, and they flow more and more, and they produce more amount of heat energy. That energy, produced heat energy, is not the application here, it is a loss. Heat energy produced due to eddy currents in a transformer core is a loss. And when you study transformer, you will mention this. In a transformer, we don't get 100% efficiency. That means all the electrical input is not obtained as electrical energy at the output. We lose some energy in the form of heat. One of the reasons for the loss of heat energy, or loss of energy in the form of heat, is eddy current loss. We are going to mention about that here. Now, eddy current produced in the core of a transformer is a loss. Now, how can you minimize this loss? Very easy method. What I can do is, that core of the transformer over which primary and secondary coils are wound. So it is like this. Core of the transformer is made into slice like this. As you slice the bread, you cut the bread, right, into small pieces, parallel pieces. You slice it into pieces. After slicing it into pieces, again it is joined. So you will have many metal plates of block. Again it is joined by using a gum. That gum is insulator. So one plate is insulated from the other plate by gumming it using an insulating gum. Because now eddy currents may be produced in this plate, but they can't flow from one plate to another. Hope you have followed, right? It is as if you are keeping one plate over the other plate, so that you will have the whole block. The block of iron is not lost, because if you don't use iron block, transformer loses its efficiency. It doesn't work properly because all the magnetic field is not linked to the secondary. Some of the magnetic field is lost, and that is called flux leakage loss. There is another loss. There is a flux leakage loss if you don't use that core. And having the intention that, sir, core produces eddy current, let us remove the core, sir. Now there is a loss due to flux leakage loss. So you must use the core. Core is used, but as soon as you use the core, you get a eddy current loss. That can be minimized by cutting the iron block or ferromagnetic block into a number of slices, and they're again pasted into form a block by using a gum, which is an insulator, so that eddy current doesn't flow from one plate to another plate. So it is made into plates like this, then joined together. So we use a simple term here, laminating core. How can you minimize eddy current loss in a transformer? By using laminating core. That's all. 2 words, finish. So eddy current is a loss, and it stops the oscillations of a pendulum. It damps the oscillations of the pendulum. Oscillations of the pendulum are damped using eddy current. Of course, sometimes it is an advantage also. If you want to stop it, use the eddy current, that's all. That's also one of the thing. And the main loss of eddy current is in the transformer core, where it produces heat energy. But that can be minimized using laminated core, that's all, simple words. What are the advantages of eddy current? So you will get 1 or 2 more questions here. Very important. Sometimes you may be asked for 3 marks also. Write 3 uses of eddy currents. If the question paper setter is very friendly with the students, you will get 3 mark question. What are the advantages of eddy current? Advantages of eddy current. Eddy currents are used in induction furnace. How do you use it in induction furnace, sir? You take a metal plate. You want to melt it, for example. I want to melt a metal plate. You take the metal plate and keep it between the 2 magnetic pole pieces, north and south. Okay? Then just turn it with this axis. Right? Turn it like this. Keep on turning. As the metal plate is like this, maximum magnetic flux passes through it. And when it turns like this, flux passing through it is less. As if we put a torchlight. And when it is like this, maximum flux. So as the metal plate turns, the flux linked with the metal plate keeps on changing, and it produces eddy currents, and it is rotated with such a high speed that the eddy current produced will produce a huge amount of heat energy, and that heat energy itself is used to melt the metal. That is eddy current. Heat energy produced by eddy currents is used to melt the metal in induction furnace. Very simple logic. Simply keep on changing the flux, that produces eddy current. Use the eddy current to produce heat. It itself produces heat. That heat is used to melt the metals. Eddy currents are used in electric meters, right? Electric meters. You remember, you go home, suppose your house is electrified and there is a meter board in your house, and that meter board, if it is containing a meter, which is the old version, nowadays we have electronic meters. In the olden days we had electric meters, right? Electrometers, which will give you the reading and you will get the bill, and it contains a disc, actually, metal disc. Of course that disc will be seen like this for you in this vertical axis, and a portion of the disc only will be seen, right? There will be an instrument like this in the electric meters, and here will be the disc. When you look from this side, you can see the disc rotating. How does this rotate? This disc rotate? Very simple. That disc is subjected to varying magnetic field. Sir, who will produce the varying magnetic field? You know, current coming to your house is an alternating current. It is AC. That varies with time, and it changes, becomes positive, negative. And what type of magnetic field is produced by this alternating current? Definitely alternating magnetic field. When the current is highest, magnetic field is highest. When the current is zero, magnetic field is zero. Current is negative, magnetic field is reversed. And such a type of magnetic field on this plate, shouldn't it produce eddy current? and that eddy current is used to made to move the rotate the disc. As the disc rotates, our meter runs. So as we consume the current more and more magnetic flux change will occur, and the disc rotates faster, more and more, and we will get more reading in the meter, and accordingly you will get the bill. So in electric meters, in order to get the reading of current and voltage consumed, that is total power consumed, we use eddy current process, wherein when the current flows through the coil or wire, that alternating current produces varying magnetic field. That varying magnetic field is used to produce eddy current in a disc, and that current is made to rotate it. And according to the rotation, you have consumed some amount of current and the meter runs. It is used in speedometers also. And before that, we will take the very important use, electric braking, smooth braking of trains. Okay, braking in trains. Electric braking in trains. How? Suppose this is a train, say, right? Say this is a train, and okay, and here you should have a magnet inside the train, and it is an electromagnet. What do you mean by electromagnet? A material which can be magnetized, demagnetized according to the current passing through the coil. So you have a very good ferromagnetic material wound with a coil, and when you pass heavy current through the coil, it gets magnetized. When there is no current, no magnetism. If you want to stop the train here, suppose this is the station, and of course the tracks pass by the side of the station. You want to stop it. What you can do is magnetize this one. Activate the magnet. When you activate the magnet, you have a magnet moving on the rails. Now these rails, when the magnet approach on these rails, right? This is metal rail, right? And as the magnet approaches towards the rails, the magnetic flux linked to these rods will keep on changing, because this magnet is approaching and approaching and approaching. Now they produce eddy current. That eddy current produced opposes the motion of the magnet. You know Lenz's law. The induced current flows in the rod in such a way that it opposes the cause. So what happens now? The motion of the train is decreased because it has to oppose. So you can have a smooth landing. So wherever you want to stop the train, even before reaching the station, at sufficient distance, switch on the magnet. That means activate the magnet by passing current to the coil. That magnet induces an EMF in the rails and produces an eddy current which opposes the motion of the train, and the train will smoothly come to a stop. Similarly, you can have some things like speedometers. In vehicles we have speedometers, right? So how does speedometer work? In the axle of the vehicle, axle will be rotating as the vehicle travels, and you might have seen that inside there is a long rod. As the vehicle moves forward, the axle rotates. Suppose you have a magnet to the axle, it keeps on turning, right? And if you have a coil here, once the magnet comes closer to the coil, and it again goes away, closer to the coil, away from the coil. So there is a current induced in the coil, and how much current is induced in the coil depends on how fast the magnetic field is rotating. How fast the magnetic flux is changing. How fast the magnetic flux is changing, how fast the axle rotates, how fast the magnet approaches and moves away. So according to the speed of the vehicle, flux change will occur, and that induces a current, and you will get the speedometer running. So there are many applications of these eddy currents, right? So eddy currents, you may be asked to write, simply mention what are eddy currents, what are the advantages of eddy currents. Eddy currents are used in electric braking of trains. Eddy currents are used in electric meters, induction furnace to melt metals, and eddy currents are disadvantageous in core of a transformer. They produce heat. But how do you decrease the heat energy produced in the core of the transformer due to eddy currents? By having what is that? I had written it. Laminated core, right? By having laminated core, you can decrease the heat energy produced due to eddy current. And I have given that one oscillating metal plate inside the magnetic field. How to decrease the eddy current there? You can do one thing. Cut slots in that. Okay, if you have north and south magnets, and if you have a metal plate like this, and if it produces eddy currents and produces damping, what you can do is cut slots over this. How do you produce slots? Like this, like this, like this. And now the area is decreased, right? When the area is decreased, automatically eddy current will decrease. So cutting slots in the metal plate will reduce the eddy current. So like this, simple mentions, and you look into the book and read the book, you will get a lot of other explanations also within this region only. You don't have anything new. So thanks for watching my class. We will meet in the next class. Already time is up. I don't know whether I have gone to the second video or not. Okay, thank you for watching the class. Keep reading, don't waste the time.